Hello, welcome to another module in this massive open online course in the principles of CDMA, MIMO, OFDM wireless communication systems. In the previous module, we have seen the MIMO zero forcing receiver. In this module, let us look at a simple example to understand this concept of MIMO zero forcing receiver. So, let us look at a simple example. Let us consider a 3x2 MIMO system, that is a MIMO system with R equal to 3 receive antennas, T equal to 2 transmit antennas. So, we have R equal to 3 receive antennas, T equal to 2 transmit antennas. Let us say this system model is given as Y1, Y2, Y3, is equal to 1 3 2 3 1 3 4 2 x1 x2, which is the transmit vector, plus of course I have my noise, which is W1, W2, W3, and this is my channel matrix, which is H, which is a 3x2 channel matrix, since I have 3 receive antennas and 2 transmit antennas. So, we can see that R is strictly greater than T. So, therefore, H inverse, that is, there is nothing known as this, that this is a matrix with number of rows strictly greater than the number of columns. Therefore, there is no H in this matrix is not invertible, that is H inverse does not exist. However, we know how to construct the zero forcing receiver. The zero forcing receiver is given as, so for this system the zero forcing we have H, the channel matrix H is equal to 2 3 1 3 4 2. Therefore, our zero forcing receiver is equal to H Hermitian H or H transpose H, since H is real, inverse H Hermitian Y bar. Let us now evaluate this matrix H Hermitian H inverse times H Hermitian or transpose, correct. So, let us now evaluate this matrix. So, let us evaluate this matrix. Now, let us first start with H Hermitian H. H Hermitian H is basically transpose, H Hermitian is the transpose and complex conjugate of H, that is 214 332 and 214 332, which is equal to, well, the product of these to H Hermitian H is 21 17 17 22, and therefore, this is a 2x2 matrix, that is a T cross T matrix, as we have previously seen. H Hermitian H inverse is 1 over the determinant of this, that is 21 times 22 minus 17 square times 22 21 minus 17 minus 17, which is basically equal to the matrix, this is equal to, well, 0.1272 minus 0.0983 minus 0.09 83.1214. Okay. And therefore, now all I have to do is now I have to multiply this H Hermitian H inverse by H Hermitian, that is equal to, therefore, that is equal to this 0.1272 minus 0.0983 minus 0.0983 0.1214 times H Hermitian, which is 214,332, which is equal to minus 0.0405, 0.1676, minus 0.1676, 0.2659, 0.3121, minus 0.1503, and therefore, this is basically my matrix H Hermitian H inverse H Hermitian, or this is also the pseudo inverse of H. So, what we have calculated now is basically the matrix H Hermitian H inverse H Hermitian, which is also the pseudo inverse of this matrix H. Now, therefore, now the zero forcing receiver is simple. The zero forcing receiver is x hat equals H Hermitian H inverse H Hermitian y bar, which is equal to minus 0.0405, 0.1676, minus 0.1676, 0.2659, 0.3121, minus 0.1503 times y1, y2, y3. On the left hand side I have x hat, which is x1 hat, x2 hat. So, basically what I have is x1 hat is equal to minus 0.0405 y1 minus 0.1676 y2 plus 0.3121 y3. Similarly, x2 hat equals 0.1676 y1 plus 0.2659 y2 minus 0.1503 y3. Alright. So, x1 hat at the receiver can be reconstructed from the vector y1, y2, y3, there is a vector y bar as minus 0.0405 y1 minus 0.1676 y2 plus 0.3121 y3, and x2 hat can be recovered as 0.1676 y1 plus 0.2659 y2 minus 0.1503 y3, and this basically is our zero forcing receiver. This is the zero forcing receiver for this 3x2 MIMO system, which we have illustrated by this simple example. So, what have we done in this case? We have considered a simple channel matrix H for a 3x2 system, which means number of receive antennas is 3, number of transmit antennas is 2. So, H inverse does not exist. So, we have constructed the pseudo inverse, that is H Hermitian H inverse times H Hermitian, and from the pseudo inverse we have constructed the zero forcing receiver for this MIMO system. Alright. So, this is a simple example sort of for a MIMO zero forcing receiver. Let us now look at another aspect. Let us look at the bit error rate of this MIMO system with the zero forcing receiver, because the bit error rate in the MIMO system depends on the type of the receiver. right now we are considering the zero forcing receiver. So, let us look at the bit error rate of this MIMO system with zero forcing reception. So, what we want to look at next is the bit error rate of MIMO system with the zero forcing receiver. Okay. And now, if you look at this, consider a channel matrix H, with all elements IID complex Gaussian with average power equal to 1. Alright. So, we are considering a channel matrix H basically in which all the elements, that is all the channel coefficients Hij are IID complex Gaussian, that is they have a complex, that is a Gaussian real part, Gaussian imaginary part with average power 1, which mean to say all the channel coefficients are Rayleigh fading with average power 1. These are IID Rayleigh fading coefficients with average power 1. So, we are considering an R cross T channel matrix. So, there are R times T channel coefficients. Further, we are considering this channel coefficients to be IID Rayleigh fading average power or average magnitude square of each Rayleigh fading coefficient is average power 1. Let the transmit symbol power P, alright. So, also consider transmit symbol power equals P, that is expected value of each magnitude xi square equals P, that is the transmit symbol power is P. Alright, the channel coefficients are IID Rayleigh fading with average power, that is independent and identical Rayleigh fading channel coefficients with average power 1, average gain magnitude square is equal to 1, and the transmit power of each symbol in this transmit vector is P. Then the bit error rate for BPSK modulated symbols, error rate for BPSK with zero forcing receptions, that is considering the zero forcing or ZF receiver, is basically equal to that of a receive antenna system or receive diversity system with maximal ratio combining, that is receive antenna MRC system, which we have seen before, with L equal to R minus T plus 1 antennas, and this is something that is very interesting and which we are not going to prove rigorously here, but which we are going to take on the face of it. What we are saying is something very interesting, that is if the channel coefficients are IID for this MIMO channel matrix, that is R cross T MIMO channel matrix, and we are using the zero forcing receiver at the ZF receiver, then the bit error rate when the symbols are BPSK modulated is basically as if we have multiple receive antennas. How many receive antennas? That is L is equal to R minus T plus 1 receive antennas, and we are doing maximal ratio combining, correct. And we know that that is the approximate bit error rate expression for approximate bit error rate with maximum ratio combining is 2L minus 1 choose L 1 over twice SNR raised to the power of L. So, this is my expression for bit error rate at high SNR with L is equal to R minus T plus 1. So, what this is saying is something very interesting. All we have to do is to look at the maximum ratio combining system, set L equals R minus T plus 1 in that formula, and basically that gives the bit error rate of this MIMO wireless communication system with 0 forcing. Alright. To understand this better, let us look at a simple example. Let us look at a simple example to understand this better. So, what we want to do is consider a 3 cross 2 MIMO system with SNR equals 25 dB, and then we want to consider the 0 forcing receiver, and question is what is the bit error rate of this system. We said the average bit error rate equals 2L minus 1, choose L 1 by 2 SNR raised to the power of L, where L equals R minus T plus 1. In this case R is equal to 3, T is equal to 2. So, this is 3 minus 2 plus 1, which is equal to 2. Therefore, the average bit error rate equals, well, 3 choose 2 times 1 over 2 SNR raised to the power of 2, that is 3 by 4 1 over SNR square. Now, what is SNR? SNR dB equals 25 dB, which means 10 log 10 SNR equals 25, which means SNR is equal to 10 to the power of 2.5, which is equal to 316.2278. Therefore, the bit error rate is equal to 3 by 4 1 over SNR square 1 over 10 to the power of 2.5 whole square, which is equal to 0.75 into 10 to the power of minus 5, which is equal to 7.5 into 10 to the power of minus 6. Therefore, this is the bit error rate of a MIMO wireless communication system with, that is a 3 cross 2 MIMO wireless communication system, that is channel matrix is 3 cross 2, SNR is 25 dB, and basically what we are computing is the bit error rate with BPSK modulation and 0 forcing receiver. Remember, the bit error rate depends on the kind of the receiver, right. For a MIMO system there are many different kinds of receivers that are possible. So, here we are calculating the bit error rate with the 0 forcing receiver, alright. And so, in this concept we have comprehensively looked at an example of a 0 forcing receiver in a MIMO system, and also an example to calculate how to calculate the bit error rate of MIMO system with 0 forcing receiver, and a simple example to illustrate what is the bit error rate of this, of a 3 cross 2 MIMO system with 0 forcing receiver, alright. So, we will conclude this module here. Thank you very much.